talk about, we started talking about decimals, and so today we're going to talk about operations on decimals. So operations, the 4 basic operations on any numbers are addition, subtraction, multiplication, and division. So we're going to be looking at some of those today, okay? And then we'll get into 7-3, which will be something else. But so the first thing that I want us to take a look at is the addition and subtraction. So with addition and subtraction, your goal is to line things up according to the decimal point. So the decimal point is matching all the problems, or all the components that you're adding or subtracting together. And you may or may not have the same number of decimals. You may or may not have the same number of whole exponents on the left-hand side, but you actually end up with the decimal in the same place. So but what I want to consider is why this works, why this is the rule, if you will, okay? So when you consider this number 4 decimal point 33 and then the 3 decimal point 26 and why it should work, that I should be able to do this lining them up, if that makes sense. I actually want to write this as 4, and then that 3 right there is in what place? What placeholder is that? That's the tens place, and we can write that as a fraction as 3 over 10. We talked about that sort of language last time, didn't we? And we can do the same thing with the next 3. What place is that next 3 in? 3 is in the hundredths spot. And then I'm going to do the 3, so this is 3, and then I've got 2 tenths, so that's 2 over 10. And I've got 6 over 100. And then if I do like we did with mixed numbers in the last section, right, I can add these, I can do mixed numbers. I can put all the whole parts together. That's the 4 and the 3, so that's 7. I can do the parts that have matching denominators 10, so that's 5 tenths. And I can do the ones with matching denominators of 100, and that's 9 hundredths. And if I write that back in decimal form, that would be 4 decimal point 59. So that's the reason that that's going to work, is because of the fractional representation that those decimals hold for us. Does that make sense? That's fine. Yeah, I don't care. It's interesting you ask that because my daughter has a real difficult time writing things in a line like that. And I know she's all younger than you guys, but I know that's okay. So if you want, I think this is what you mean. Let me just make sure that this is what you mean. Am I on the right track, Audrey? Yeah. Yeah. So Audrey's asking if she should write it like that. That's fine. It's all in addition.
Okay, so you do want us to like separate them?
Well, no, I'm just showing you how it works. Okay, so the problem asks you to explain why it works. Yes. I would expect to see you write it all out. We're going to do another problem here in a minute. Well, next problem. Let me see. So here's one. A stock price dropped from $63.28 per share to $27.45 per share. What was the loss on a single share of stock? So what am I going to do with these numbers? Subtract. And I'm not going to show it all out because that's not the problem asks. It just asks to see what happened to the stock, right? So I'm actually going to subtract $63.28 minus $27.45. And we're going to subtract just as then we would have subtracted with whole numbers way back when we learned whole numbers. And if you haven't taken Math 1, that's something we cover in that section, some of the other methods. But the most common method that you probably remember is that we do things called borrowing, right? So the first one I don't need to, with 8 minus 5, 3. And I do expect to see the borrowing if you're going to do it. Okay, so think back like what you were doing when you were in 2nd and 3rd grade. The 2 is not big enough to subtract from, so I need to change the 2 to a what? A 12. And the only reason I can do that is because I'm borrowing from this place here. This 3 becomes a what? A 2. Now, just in case you haven't had Math 1, so you don't understand why that is actually working for you. The reason that's working for you is imagine what you're doing. This is in dollars, so this is a really easy way to describe visually what's happening. You're taking $1 away, and you're turning that dollar into what? 10 dimes, right? You're turning it into 10 dimes, and you had 2 dimes to start with, so now you have 12 dimes total. And that's literally what you're doing. Okay, so you're making changes in cash register at the store kind of thing, okay? So if we do 12 minus 4, then I get 8. 2 minus 7, that's still not going to work, so this 6 is going to have to become a 5. Again, so it's like I'm taking away $10. I'm turning the $10 into 10 ones. So now I don't have 2 ones, I have 12 ones. 12 minus 7 is 5, and then 5 minus 2 is 3. So make sure you answer the question, what was the loss on a single share of stock? It was a dollar amount, $35.83. So make sure you're doing the dollar sign off. Does that make sense? And I think that probably should be the question I remember. Okay, good. Multiplication. Well, you probably remember how multiplication works too. Everybody seems to like decimals mostly. Fractions maybe not so much with decimals, we all seem sort of, I don't know, they're more fuzzies or something to us. So when we work with decimals, you multiply as usual. You multiply your numbers. But then you count the number of decimal places, and your final answer has that many decimal points, or that many places after the decimal point. So you multiplication. In other words, if we were doing this problem with these directions, I would say 7 times 3, that's 21. And I would say, okay, there's one decimal point here, one value after the decimal point here, that's 2 values after the decimal point, so my answer has 2 values after the decimal point. That's literally what I would do. But it kind of looked like magic. How about you? The rule you memorized, and we know that's a little bit, kind of looks a little bit like magic, doesn't it? Why does that rule work? So let me show you why it works. We're going to show you why it works in terms of fractions. This is why we actually talk about fractions before we talk about decimals. How could I write 3/10 as a fraction? 3/10. And how can I write 7/10 as a fraction? 7/10. And in the last section we learned about fractions, and what we said when we do fractions is that we can multiply them together how? Across. Okay. So if we multiply across the top, what do we get? 21, and across the bottom? 100. And is that not another representation for our decimal point 21? Yeah, that's 21 hundredths, just like the decimal point 21 is 21 hundredths. So this is why this method works, is it's pulling us back into those fractions that we already learned about. Okay? Division. Oh, another magic moment. Division. So when we do division, you have this idea that you sort of set it up like regular division, right? You write the division bar, you put the number on the outside, the number on the inside. And what you do is you take the number on the outside and you somehow turn it into a whole number. You move the decimal point. And wherever you move the decimal point on the outside, you have to move the decimal point that many times on the inside. Again, or not. So let me show you how that works in terms of what I just described. The value on the outside is what you're dividing by. The value on the inside is what you are dividing. And then what you do is you take the value on the outside's decimal point and you turn that into a whole number by moving the decimal point. So if I move the decimal point 2 on the outside, I have to move the decimal point 2 on the inside, and then I do my division like normal, right? How many times does 5 go into 75? That's the question. 15. So you probably do 1, and you do 5, and you subtract, and you do 25, and you do 15. That one's not probably hard to figure out. You just know that, so, right? You know, okay. All right, so the kicker is then why does it work? Okay? So take a look at this. This is actually, I'm going to write it in fraction form. So let's take this. This is 0.75 over 0.05. Okay? Well, the idea in what we just did on the other division problem on the side there is we want to take whatever's in the denominator, it's currently my denominator, on the outside of the division and turn it into a whole number. Right? Well, how do I turn the decimal 0.05 into a whole number? Literally, what do I really do besides move the decimal? What am I really doing? I am multiplying by 100. That's exactly what I'm doing. And you know that you're allowed in working with decimals and working with fractions that you can multiply the denominator by 100 if you do it at the top too. We call it. It is an identity. Yeah, it is a multiplicative identity. I think we had another name for it when we were working before, but yes, it is the identity of 1. As long as it's top, it's the bottom, that's a fraction of a value of 1. Yeah. All right. So then, if I multiply 0.75 by 100, I would get 75. And if I multiply 0.5 by 100, I would get 5. And then if I divide, of course, I will get 15. But that's what you're really doing when you're moving decimal points. When you're moving decimal point, anytime you're moving a decimal point, just literally moving this, you're multiplying or dividing by some power of 10, depending on which direction you move things, right? If you move in one direction, you're dividing, and if you move in the other direction, you're multiplying. So that's literally what you're doing, is you're multiplying this case by 10. So I'm going to actually write what I just told you down, because I think it comes back up again in your homework. Moving decimal points. Is, and I'm just going to say multiplying, because I'm going to say multiplying by a power of 10. Now, that power may be negative, and if that power is negative, then that's in essence dividing, but you can sort of include that all the way. So multiplying both divisor, and that's what you're dividing by, which is equivalent to my denominator, and dividend, that's the 75 here, that's 0.75. Dividend is equivalent to my numerator by the same value leaves the quotient unchanged. Surely not. Yes, by a power of 10. Yeah, it is very similar, because we had probably got ratios like that, didn't we? We had the ratio of boys to girls in the classroom, that was 5 to 6, or something like that. So we said that there's 11 students in class. Yeah, it's very similar to that. Yeah. That's too many. All right. And this whole idea of moving decimal points is so well when you talk about scientific notation, which is why this occurs. So there's a lot of text on this slide, okay? So I don't want you to write any of this. Let's just kind of talk through what it's saying. So the basic form for scientific notation, you've got some number times 10 to the power. That number in the front, that A, has some properties. It has to be between 1 and 10, okay? It can have decimal points, that's fine. That's fine, but it can't be any smaller than the number 1, and it can't be any bigger than the number 10. In fact, it can't equal 10 either. So it's actually including 1 and not including 10. The exponent is an integer, okay? So integers will remember positive and negative whole numbers. So you can have something like negative 7, but you can have something like 4.6. Okay, the exponents actually have to be a whole number, but they can be positive or negative. So that's what scientific notation is. We want to be able to both go from our notation, the standard, how we normally write things, into scientific notation. We also want to be able to take something that's in scientific notation and write it back in standard notation. Now, you might sort of feel like, make sure this is on my questions. No, it's not. You might sort of feel like, some students must ask me, what's the point? Why do we need scientific notation? Scientific notation is used in primarily 2 situations. Those situations when something is really, really big, so think the size of the universe. Okay? I don't want to write how many miles it takes to get to Mars. I don't want you to do that. I mean, that would be ridiculous, right? And something that's really, really small, so think chemistry, right? Size of an atom, size of a proton. Again, I don't want to write a decimal with a whole bunch of zeros before I actually get into any numbers that are not 0. So all scientific notation is a condensed way to write things that are really big or really small. Now, obviously, there are some times when we write scientific notation or the calculator spits back out into scientific notation, and it just doesn't make any sense to express it that way. If I have $100, it doesn't make any sense unless I have $102. It doesn't make any sense for me to tell you that I have 1.02 times 10 squared dollars. Who talks like that? Nobody. It's talking about money, right? I mean, we don't do that. There are situations where, of course, it's absurd. We don't talk like that. But there are situations where it's really valuable. how to go back and forth. So let's talk about the standard one first. We go from standard, that's our numeral, into scientific notation. Our goal is to take our number, however it is, and put a decimal point in it in a good spot. That decimal point needs to create a number that looks like A's directions, a number between 1 and 10. So we put a decimal point in a very desirable location. And then what we have to do is we have to figure out where the decimal point really was to start with and then count. Okay? So we'll do it in a minute. If the exponent is a positive number, it meant that you had a large number to begin with. So if you have a large number, so if I had 5,467,236, big number, right? And I changed it to 5 point something, because that's what I would have if I put the decimal point in that desired location. I took something that was a large number, which means that when I expressed it in scientific notation, the exponent was positive. This is large. Okay? If I took something that was really small, like the original percent decimal, 0.00376, okay, well I take that, it was a really small number, and I put the decimal point in after that 3, my exponent needs to be negative, because the number was originally very small. So you should sort of have this relationship in your mind between small numbers and negative exponents and large numbers and positive exponents. Because if you have that idea, then I don't have to worry about to move the decimal point left or right because the exponent is positive or negative. And which one is it if I move from scientific to standard and standard to scientific? Because you get all mixed up. The idea is to have a conceptual understanding of what those decimals mean and what the exponents mean. Positive exponents mean large numbers and negative exponents mean small numbers. So if you're looking at taking something in scientific notation into standard notation, and you have an exponent that's already positive, what it means is that the expression is going to look bigger when you're done. And if you have an exponent that's negative, it means the value you have is going to look smaller when you're done. Okay? Positive exponent, large number, negative exponent, small number. So let's take a look. We're going to convert this one into scientific notation. So somebody tell me first, is it a big number or a small number? It's a big number, right? 298,000, and if you don't think it's big, then you can head me that much money. I'll take it. So, it is a big number, yeah? So I'm going to write the number out without the zeros. And you tell me where my decimal point goes. After the 2. I need my decimal point to go in the location where the number that I get resulting with is a number between 1 and 10. And this is. Good. The next thing I do is I put that it's times 10 to a power. Now the first thing I want us to ask ourselves is the power positive or negative? Positive. Why, Sarah? Because it's a big number. I'm going to have a positive exponent. The value of the exponent is exactly the number of decimal points that I moved. The original problem had a decimal point here. Right? After the whole value is over, because I didn't have anything after that. If I count, I moved it 1, 2, 3, 4, 5. 5 decimal points, that's my exponent. And it's positive because my number is big number. So there's scientific notation. Positive exponent is big number, negative exponent is small number. So number 3, am I going to end up with a number smaller or bigger than 3.2 when I'm done? Smaller. It's the negative exponent, right? So I'm going to start by writing the 3 and the 2 out. And I know it's going to be smaller, which means I need some zeros in front. That's how I'm going to get it to be smaller. I don't know how many I need exactly, but I'm just going to put a few in there. Now the original decimal point was right here. And this negative 5 tells me exactly how many decimals I need to move it over. I need to move it 5. And I'm moving it left because that's how my number looks smaller. So I'm going to move this decimal point 5 to the left. So this is 1, 2, 3, 4, and 5. So my decimal point followed by 4 zeros and then a 3, 2. And that is the standard notation for that particular scientific expression. Okay? So there is no actual multiplying out. I know that said times 10 today. We didn't really multiply, right? Not really. The decimal points are the equivalent of multiplying. That's all we're going to have to do is to move the decimal points. Right? Now the next one's a little bit more interesting. Is it very good if we switch to the slide? Because it has some legitimate multiplication geometry problems. I actually have 2 different expressions in scientific notation that are multiplying. So when I'm looking at this particular problem, I need to do kind of like what we did when we did mixed numbers with addition, right? We can actually take the components that are not the times 10 whatever and we can combine them. In So I've got, and I'm going to kind of just reorganize, 8 times 6, and then I've got 10 to the 12 times 10 to the 15. So the first thing we're going to do is 8 times 6, and what do we get? 48, you betcha. Okay, now I've got a 10 to the 12th and a 10 to the 15th, and this is properties of exponents. How do I combine those? Add the exponents, you do. This is 10 to what power? 27. Now, we've done all the actual calculation here, but we're not quite done. What's wrong with this as an answer to this problem? Yeah, it's not in scientific notation yet. Scientific notation, I shouldn't have 48 at the front. That's not between 1 and 10, right? I need something else. So what number should it be at the front? Right, it should be 4.8. Now here's your question. Is 48 a big number or a small number? Oh, I put 9. Thanks. It's a bigger number than the line I just wrote down, right? So what does it mean? Well, it means my exponent would get bigger. Right? How many bigger? 1 bigger. So instead of it being times 10, I'll use the times there, times 10 to the 27th, it would be times 10 to the 28. Then it would be, it would just be like 4.8. It would, that's right. And literally, if I wanted to write down 4.8 times 10 to the 1, then I can find 10 to the 1 and then 10 to the 27, and then I get 10 to the 28. Yeah, that's right. Any more questions about this one? Okay. All right, rounding. Do you guys remember rounding from elementary school? Yeah. I have a distinct memory of talking about rounding and estimation, and my mom being very confused. Because in her mind, what she wanted to say was that you should always round up, like if you would do things in the grocery store and you had to pay your bill. So rounding $32 down and giving the clerk 30 would not be appropriate, right? Of course, that's not what we mean when we talk about rounding. We do have some very specific rules that we follow. So when we're looking at rounding, we always round to the nearest length, and we have to talk about what it is we're rounding to. Are we rounding to the nearest 100, or are we rounding to the nearest 100th, right? And then we have the whole gas station thing, which is just a fiasco because they give us extra decimals beyond what we can use for money, which is just weird. But, you know, that aside, normally with money we've got rounded to nearest 100, right? Not 1,000 and so forth. All right, so we find the location that we're rounding to, and then we look 1 decimal point to the right of that. If the number is 0 to 4, then we round that number down by making everything else zeros. And if the number is 5 to 9, we round the decimal point we're looking at up and we make the rest zeros. Everything else becomes zeros. But you may or may not have heard of front-end estimation. Have you heard of front-end estimation before? Okay. What front-end estimation does is, again, you need to know which number you're looking at. So the first number, or the first 2 numbers, or whatever. And it just keeps those numbers the same, and it wipes everything else out and turns them into zeros. So I don't care if the next number is a 9, everything turns into zeros. It's not rounding, it's estimation, front-end estimation. Okay. And we're going to do an example so you can see how it will work. So we're going to use rounding, we're going to use front-end estimation to estimate the following. Then we're going to actually perform the computation and see how close we are. Okay. So we're going to do basically 3 things, right? The first one is rounding, and it doesn't tell us what to round to. So we need to pick. We just need to pick the same thing for both of our part A and B. So we can pick rounding to the nearest 10, or probably rounding to the nearest unit. So we're probably wanting to change these into something like 80 or 90 and 30 or 32. Or we're wanting to change these into, or we're wanting to change these into 89 or 90 and then 32 or 33. We just have to decide how many points do we want to keep. So do you want to round to the nearest 10 or to the nearest unit? Unit. Sarah says unit. Okay, so on your homework you get to pick. There are too many more specific directions than you get to pick. So Sarah's wanting us to do the nearest unit. Okay, which means we're going to have 2 points, and then we're not going to have any decimals when we're done, when we're doing the rounding, right? Okay. So here's part A. Look at here. So if I took 89.47 and I want to actually do rounding, I use the 4. and I say, oh, there's a 4 there, which means I do what? I round it to 89. So I round 89.47 down to 89. And then if I do 32.16, I look at the 1 right here, and I say, okay, there's got a 1 there. Well, there's a 1 there, which means I do what? I round down to 32, right, let's see, yeah. And then if you take 89 minus 32, what do you get? 57. Now, because we're rounding to the nearest unit, this problem becomes very odd. Okay. I'll show you what happens when we do the tens in a moment too, so you can see there's actually a difference. If you're rounding to the nearest unit, we get the 89 to 32. If you're doing front-end estimation, what it means you do is you would flat out ignore the 4, 7, and the 1, 6. They just aren't there. You don't look at what they are, you don't care what those numbers are, it makes no difference whatsoever. All you do is write down the first 2 numbers, regardless of what comes next. On this one, it happens to be that that's the same set of numbers. That's what happens when you let students think. You should honestly see the difference. I'll show you the difference in a minute. Yeah, so this is a big 57 as well, right? And then part C is to actually do the subtraction. So at 89.47 minus 32.16, which is actually really friendly because then you have to borrow, right? 7 minus 6 is 1, 4 minus 1, 3, and then I have the same 57 I had before. So obviously it says to see how close your estimates are. My estimate's really close. I think I could live if somebody did not give me back 31 cents that they were supposed to, right? You'd be okay. Okay. Let me show you what happens if you run the nearest tens. Because I need you to see that there really is a difference here. All right, so let's look at 89.47. What is that rounded to the nearest tens place? That's 90. And what is 32.16 if you round to the nearest tens? That is 30. And 90 minus 30 is 60. All right, part B. 89.47, front-end estimation says I write the 8 down, and everything else becomes 0. It just goes away. So my 89 actually turned into 80, which doesn't seem very close, does it? Not so close. And then my 32 will become what? 30. And of course, 80 minus 30 is 50. So that's what front-end estimation would look like on this particular one if we use it to the tens place instead of the units place. And I'm not going to do parsing, it's exactly the same. Okay, now we're going to round as specified. So we actually are told what to round up on this, and we don't get a thing. All right, so let's see. We've got 203 and 651 thousandths. That's how we would say that. What would we get if we rounded to the nearest 100? 200. What's different on part B? I got the TH at the end and it matters, right? The 100th location would be where my 5 is currently, right? So what would I get if I round to the nearest 100th? Right, 203.65. Which looks more like our money, right? If you multiply something, this is what cashiers not, they don't literally do, that's what their machine does, right? It takes that 1 at the end, they would ignore it at this point. But if that 1 at the end had been a 6, they would round up and they would charge another penny. That's what the cashiers are supposed to do. Okay, they round to the nearest 100. How about the nearest unit? What would we get if we rounded to the nearest unit? What is it? 204. So the unit place is where my 3 is right now, and the 6 to the right of it is bigger than 4, right? It's 5 or bigger, and so we would round up to the 204. All right, so here's an interesting question. This is kind of like the type C questions that your book does. In fact, it is for your book's type C section. A student tries to calculate 0.999 to the 10,000th on the calculator and finds that the answer is 4.5173346 times 10 to the negative fifth, which is almost 0, right? Negative fifth, it means this is a really small number. The The student wonders how it could be that a number like 0.999, so close to 1, you practically got off the number 1 there, when raised to any power, some power, results in a number so close to 0. How do you respond? Any thoughts? So you can think about it in terms of fractions, right? So what happens when you multiply fractions together? And I think you mean proper fractions as you say that, right? Yeah. So what happens when you multiply proper fractions together? Okay. The number gets smaller, right? So when you multiply, so let's not look at 0.9 for a moment. Let's look at another number. Let's say that the number 1/3. Multiply 1/3, and power is being multiplied when you by itself. So if you multiply 1/3 times 1/3, we would end up getting 1/9. So as the fractions get multiplied together, they actually get a smaller product. Yeah. That's a good way to describe this. There's another issue going on as well, because his issue isn't so much that it got smaller, it's that it's nearly 0 as well, right? Why is that happening here? Well, but why is it so small? Why is the result of doing this problem so small? What's the exponent? No, the original exponent. 10,000. Consider my example. One where I said 1/3 times 1/3. We just did it twice, right? We just did 1/3 squared. This would be like doing 1/3 10,000 times. And every time, like Sarah said, it gets smaller. Smaller and smaller and smaller. The pieces get smaller and smaller, right? What happens if you keep doing this infinitely many times, or 10,000 times in this case? Yeah, you get nearly 0, don't you? That does seem reasonable. In fact, I want to give you some examples specifically of what happens. So let me put what you were saying first down here, because that's what I have written down for us to write down first. So whenever you multiply by, and I'm going to use it in decimal terms, so by a value less than 1. That's the proper fractions that we do in our talking about, right, Sarah? Proper fractions, values less than 1. Your product becomes smaller. And in this problem, multiply technically 10,000 times, so a bunch. And one of the things you can consider, and I'm going to write the gist of what you could do. You don't have to actually do this with me, but if you were to take your calculator and you were to do 0.999 in your calculator and square it, okay? It's going to get smaller, first of all, very said that it is, right? It's not going to get smaller very fast. This is not going to be dreadfully smaller. But just to give you kind of an idea, this gives you 0.998001. It's a little bit smaller, but that's just doing it one time. Okay? So let's then square that. So if I took the 0.998001 and I squared it, your calculator would do that. You just hit the square button. Okay. You would end up getting 0.996. Whoops, that's not this decimal point. 006. Again, a little bit smaller. Yeah, of course, we already said that. Yeah. And we're going to do this a few times. So I'm going to keep this process up, and I want to show you what happens and how quickly it even does. So this is the first time I squared it, the second time I squared. The next time I get 992,028. And then you might be thinking this is going to take all day. I promise it's not. 984119, and I'm just using 6 decimal points just because that's what I should use to show you. Okay. And then I'm going to get 0.968491. So what am I doing now? 5 times. And then I'm going to get 937,975. Bear with me just a little bit longer. The next one is 879797, and then 774043, and then we just take a notice tag. 599142. That's the last one I'm going to write. 358971. And all I did every time is I hit the squared button I have there. I squared the previous result. I squared the previous result. And if I counted up, I think I did it 10 times. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it took 10 times of the squaring process. And I'm going to value less than a half. Right? And you can see how quickly they're plummeting at this point, right? A huge drop at the very end there. It looked like I was barely moving at the beginning, and now I'm just dropping like a bombshell. So it only took 10 times of squaring